So, streaming. Yep. We are back after a bit of a long break. And that actually feels painful, to be honest, because I know I worked on the first pages of these, but really, really have to do a bit of a recap. Let's just go to Twitter first and say hi to the people. See if anyone wants to join. So let's go. Twitch. I should have a button to just copy paste the URL. Twitch.tv/uncertain systems is now the thing. Yep. Cool. I'm really still trying to figure out a lot of these things and where do I want to take this whole thing. I've changed a lot of stuff along the way since I started the whole YouTube thing, and now it's really more like the whole Twitch stream and kind of like live research, live learning. I mean, it's and research in sort of the purest sense and sort of the most innocent way, right? It's just like just trying to. I mean, what's the research definition? Like, can I get something in English, please? How can I change the language of these? I know I'm in Germany. Isn't there like a language thing somewhere? Oh, there is a language or something. English. Cool. The systematic investigation into and study of materials and sources in order to establish facts and reach new conclusions. That's what I want to do. So I'm kind of doing research, live research. Anyway, yeah. I saw. Come on, get off the chat. I just saw it. I just saw the messages. I'm just not gonna open Slack now. Discord now. Mm. So we're here to dig into the path integral stuff, and I got a bit more time today. So let's see. Let's use it. Let's use it a bit more efficiently. And I'll have to kind of recap a bit. So thank you. Thanks for the best learning wishes. Again, so the overall goal here is try to understand entanglement from the path integral picture. Although the more I've been thinking about these, the more I kind of realized, like in the past days, like these might just really not bring me anything, because I sort of realized that entanglement is like part of the static picture, right? So you've got a state, and then that state is entangled. Like, of course, you can think about transformations from like one state to another and whether the transformation is actually entangling and how that entangles. So maybe that's a way to define it or a way to model it. Yeah, maybe that's not such a stupid idea, right? Kind of think about like think about a state transformation and how much entangling is that operation, right, or that transformation. Because at the end of the day, I mean, I really don't know anything about the path integral stuff, but at the end of the day, I kind of think that doesn't really change, right? You're still operating with wave functions. That's kind of still the state representation is kind of the same. So I don't think that we're gonna get to anywhere meaningful. But let's see. Let's just really go through all these, and let's just maybe do a high level run first. Not stopping much where we don't understand things, and then kind of come back to these, because this sometimes is useful to cover a bit more territory. Because last time I got stuck here, right? I got stuck here in terms of understanding the Okay, so what was so the whole thing with the Hamiltonian. So given a trajectory, so okay, associated to transition probability amplitude with the same form as given Dirac. Of course, by quantum mechanics, we cannot speak of the particle taking a well-defined trajectory. So and then here's where the integral comes, right? And this is where the name path integral comes from. So if the quantity can be calculated in the method suggested by Feynman, the time evolution of the state can be determined by considering contributions from all the possible future states, and the problem is solved. So below, the kets are eigenstates of the position operator, such that integration over all x spans the entire basis. And I kind of got stuck a bit here because I was like, what are we really integrating here, right? So we're saying that the wave function with respect to x and t prime, t at time, at time t prime, it's the same like integrating across. And again, that's sort of the projection, right? So you're integrating over all the probability that from an initial state at t0, x0, that if you calculate the projection, so the probability, and I guess what was hard for me to understand is like how is time factored in here, but it's just part of the dimensions. So it's really like space time if you want to think about it, right? So that's why it's the wave function is a function of the position and time. So the orthogonality of these wave functions mathematically should tell you whether it should really tell you whether you can ever reach that point from this one, right? So what the probability is. But then I really couldn't grasp what is that other thing doing here. But let's go forward. So known as the path integral formulation of quantum mechanics, it gives the same results as those dictated by Schrödinger picture, eliminates some of the deeper aspects of quantum mechanics. In this paper, we'll present the method. What are these deeper aspects, though? That's what I'm curious about. So though it is pedagogically backward, we'll then demonstrate the use of the method before showing its equivalence to the Schrödinger picture. We will then investigate the method as applied to the harmonic oscillator. Following these, we'll introduce the concept of Euclidean path integrals and discuss further use of the path integral formulation in the field of statistical mechanics. So, path integral method. Define the propagator of a quantum system. Okay, so let me just focus. Define the propagator of a quantum system between two space-time points, x prime t prime and x0 t0, to be the probability transition amplitude between the wave function calculated at those points. So you have this. Okay, so you build this propagator of a quantum system, which is a function of 2 points. And so it basically tells you what the probability is that it transitions from that wave function to that wave function, right? And maybe, again, let's try to kind of reconstruct these on the go with a little bit of paint magic, right? So, what do I really want to do, actually? It's just like, what? Like, would you say something like Cool. So let's say my wave function, the the problem is that I'm too much. What am I doing? I'm too much like I have too much like built in the whole thing of quantum mechanics, right? And just using like the kind of just saying like, for example, this being wave function is like, and then the propagator will be like, so can like at time, this time zero, like at time one, sort of the next moment in the circuit or something, can this be like, can this be the blast state, right? Um, I guess that's so you'd basically have. It's a bit confusing that this is defined like this because like this will obviously, like if I were to just use the state 0 and 1, this will obviously give me 0, right? So I'm not sure I understand what the objects here are. I mean, they are wave functions at a given position and time, right? So, so how can you just do the product, sort of the projection? I kind of have a hard time understanding that this is the right way to model things. So if the Hamiltonian carries no explicit time dependence, we can relabel the first time value t0 equals 0 and work only with the elapsed time t prime minus t0. We will often write 3 as x prime t and x0 to illustrate this. A propagator above, along with an initial state ket, fully describes the evolution of a system over time. Okay, that's probably why, yeah, so that's probably why these is these here, right? So the idea is, okay, so the idea is this gives you a complex amplitude. Well, this gives you a complex coefficient, and that's why you then multiply it by these. So for all x primes, yeah, okay. So the wave function at point x, yeah, just confusing notation. Or it's confusing me at least. Mm. So if the Hamiltonian carrier will often write, sorry, this is the propagator above along the initial state ket, fully describes the evolution of a system over time. It is also customary, as is done in Sakurai, to use here the symbol K instead of U and refer to as the kernel or the Feynman kernel. The path integral method, as we're about to see, is an explicit way to construct this propagator. Okay, so we consider possible trajectories xt. Okay, so the whole thing is about how do we construct this propagator. That's what the whole method is about. We consider possible trajectories xt of a particle moving through a time-independent potential Vx with endpoints fixed at x0, t0, and x prime, t prime. An infinite continuum of such trajectories are possible, each with classical action. Okay, so this is okay. So now what we're doing now is we're saying we've got like a um, sort of, I think the physicists always say time goes vertical, right? So time and position. So it's a space-time, two-dimensional in this case, right? So just one space dimension, one time dimension. Um, so let's say here is, x0 t0, and here is x prime t prime. So it's another position at another time. Um, and so and then there's another function, right, which is the potential that basically it's kind of like a field in a way, right? So for every point of x, well, not a field, okay, it's time independent, so it's really just a function of x. So this means there's a third dimension to these, right, which is what the potential is, right? And so that might be like, that's actually another, like, that is v and that is x, right? So you have, and these x is these x, and so I don't know, like, do they say it's constant potential, or do they just say it's like um, time independent potential? Okay, so it means it doesn't change in time for a specific position. So that's why we ignore the time dimension in here. Otherwise, it's going to have third dimension. But it doesn't say it's constant. So, but it could just be like, it really could. Okay, so it's fixed between these two endpoints. So it could really just be the endpoints fixed. Okay, so what we're saying is that at x0 and at x prime, this is this is where we define the potential. Like everything else, we don't care. So here's like you would kind of say, here's the potential. Like we just could be constant, could be like these, whatever. Like, cool. An infinite continuum of such trajectories are possible, each with classical action yx of t. So each trajectory has a classical action as, hey, I got bros, what's up? Yeah, doing a bit of a live learning slash research, if you want to call it this way, just trying to kind of understand a bit more about the path integral stuff. As I said at the beginning, it was just really kind of as part of my kind of goal to try to understand a bit more entanglement from different perspectives using different models, right? Um, yeah, yeah, I'm a brave man. Never done any of these. It's fun though. It's fun though, and it's part of the whole thing with the entanglement project as well, right? So trying to understand entanglement from different perspectives, and it's kind of like, from the Schrodinger picture stuff and all the quantum computing stuff that I've done, I think it gives me a good picture, but I just want to try to look at it from different perspectives, and that's kind of what I'm trying to do, which is, trying to go from one picture to another, or at least understand the path integral stuff, because that also really relates to the way that Wolfram is doing the same thing with the whole hypergraph stuff, right? So I'm kind of curious how all this connects, and so we'll see what that takes. But that's gonna be definitely a long journey, as I've never done any of these. I mean, all the physics that I've ever taken is just like classical physics in high school, and some basic stuff in the university at the very beginning. But that was just basic, really, really, really basic stuff. Cool. But I need to recap what the whole thing with the classical action is. I did read a bit about these, but yeah, okay, cool. It's good to know. Yeah, I don't know. It just, it's, and to be honest, I just picked the first random thing. I found these notes from MIT, and like that's also sort of the whole thing, right? So the whole thing is not to just follow like a traditional kind of curriculum or like a traditional path and structure way to learn all this stuff, but it's rather saying let's take Wolfram's model, which is like they're trying to actually model everything, right? And see if we can use these as a guide to actually learn more about physics and all this kind of stuff. And then and because it's fairly new and it's something you have to continuously challenge, it keeps you like I think challenging yourself as well. And then but then I kind of cherry pick things from different places, maybe referenced in Wikipedia and whatnot. And I don't know, I kind of came across these last time, but I had a bit of a break between the last session and this one, so kind of having a hard time now. Um, yeah. But I need to. I did do a month or two ago. Did dive into the whole classical action Lagrangian stuff a bit more, and I think I need to refresh these. Um, I kind of seem to understand this. If I understand this correctly, so it's the what this is just saying, right, is that you can have like if this is your if this is your quantum your wave function at x0 t0 and the wave function at x prime t prime, you can have an infinite amount of paths between these 2 points, right? And that's kind of the typical picture you see when you just Google path integral. And then each path is associated to a classical action, to an action, right? And so, and I think that in Wikipedia there's quite a good so the action is a numerical value describing how a physical system has changed over time. So it's significant because the equations of motion, blah blah. So yeah, this is the whole thing with the principle that you take the path of where the action is minimized, right? But I guess you get to define action yourself, right? Eric Aspling, who's Eric Aspling? Oh, sorry, is this the person who's who wrote these? I'm sorry. No, who's Eric Aspling? Let me Google. Oh, he's got like I think I've seen some of his videos, or at least some of the videos. It's like okay, it's a physics content creator. Okay, cool. Yeah, I don't know. I don't really consume a lot of content, to be honest, because I sadly don't have the time. I should probably plug some more video content into these as well. Kind of watch some of these related sessions, maybe as part of the study and learning sessions. That'll be that'll be good. So the action, but so you get to define the action, right? So it's in simple case of a single particle moving with a specified velocity, the action is the momentum of the particle times the distance it moves, added up along its path. So lines of time, which has the amount of energy added up over the period of time of the consideration. Why would that be? So okay, yeah, because the action, I remember that. So the action is supposed to represent how much is something changing, right? So it's got to include the change in energy. And so the momentum kind of gives you a relation, or it gives it kind of gives a connection to the kinetic energy, right? Because I remember the whole thing with the action just being in general like kinetic energy minus potential energy, something like that. There's like a minus a plus sign. Okay, Okay. Yeah, cool. I don't know. I mean, for me, it's like, I started the whole um, YouTube channel as a let's learn quantum computing live kind of thing. And I just started it on YouTube. I don't know why, to be honest. I guess it's just because I didn't feel like streaming was the easiest thing to start with. But then I realized that like I'm not the kind of person that curates and kind of like likes editing videos and whatnot. And I kind of really wanted to, I really treasure and kind of wanted to show and share this kind of like aha moments when you really truly learn something. You kind of connect the dots and you're like, it snaps and you're like, oh, okay, that's it. Like now I understand that. And you can't just edit that, right? Like it's not the same. So sometimes when you get it on camera, it just like I think it's also inspiring for others. And so at some point, I kind of realized that I had gotten from in a way 0 to 1 in quantum computing, from whatever that means, right? It just felt like I was at a moment where I was kind of intermediate level, and I just wanted to do something a bit more in depth, and that's when I started with the whole entanglement stuff, and then that brought me to this as well, to kind of try to dig a bit more into the quantum mechanics stuff, right? But anyway, um, yeah, yeah, yeah. I mean, that's why I kind of like when you guys also do a bit of the more kind of like raw thinking and stuff in the podcast. It's just I think it's yeah, it's quite authentic. Um, and one really kind of gets the vibes as a listener. It just feels like you're there in the conversation, which I think it's something that is really rare. And it's scary, right? Because it's a bit scary because it feels sometimes like it's almost like too private, right? Like it's easy to make mistakes and just look dumb on screen. But I mean, the truth is a lot of even the experts struggle with a lot of stuff. So anyway, action. It was kinetic minus potential or something like that, or plus potential. No, minus potential, I think. So so yeah, it takes a path of evolution. Doesn't have to be physical path, right? And then it gives you a real number as a result. A real number doesn't maybe necessarily. So what it means is the change over time. And so the whole thing with the principle of stationary action, right, is that physical systems tend to follow the paths that minimize the action. But that's something that you kind of got to define for each system, right? So and now let's go back at the paper here. So what Mr. Feynman's saying, so we're saying is there's all these different trajectories that a wave function could take, and it's not necessarily physical movement, right? But it's like the evolution, right? Like in each point you have a different wave function, so it's evolving from this wave function, and it can just evolve in or this state, right? So it goes from this state to like one state, or maybe even a superposition of states, right? As a sort of in yeah, that's a fact, that picture. I'd say if you say you take the slice of time, here you have different possible states that it could be in superposition. As an example, I don't know. Or I guess you could think of each of these paths independently. But yeah, and then each of these paths that go from one place to another has got an action. And what we're saying here is that this action um, the contribution to the propagator from a particular trajectory, and the propagator is then the function that tells us what is the probability of the transit of that path being the path that's followed by the party by the system, right? So what Feynman's saying is that that this is the contribution, and he is like, okay, so these thing here is the action of the path. So it's e to the power of I times the action divided by h bar. Welcome to like the messiest thing in the world. I mean, like the whole thing with e to the power of things and e to the power of I, like complex numbers, right? That's got to do with rotation somewhat, but I don't really. I think Three Blue and Brown had like a good video about this. Um, E power I or something. Yeah.
One
I
way to
hope
think about
I
the
hope
function e to the t.
I think that I got the setup correctly, so that the audio is also going through the stream.
The defining property is that it is its own derivative. Together with the added condition that inputting 0 returns 1, it's actually the only function with this property. And you can illustrate what this means with a physical model. If e to the t describes your position on a number line as a function of time, then you start at the number 1, and what this equation is saying is that your velocity, the derivative of position, is always equal to that position. The farther away from 0 you are, the faster you move. So even before knowing how to compute e to
Cool,
the
thank you.
t exactly, going from a specific time to a specific position, this ability to associate each position with a velocity paints a very strong intuitive picture of how the function must grow. You know that you'll be accelerating, and at an accelerating rate, with an all-around feeling of things getting out of hand quickly. And if you add a constant to that exponent, like e to the 2 times t, the chain
Harmonic oscillator. Yeah, but I mean, what's that got to do with that? I'll get there at some point, I guess. I mean, they're gonna do the harmonic oscillator stuff with the path integral as well at the end of the paper, so I think that's pretty interesting. But I guess what I wanna, because I remember watching these, and I think it's interesting here where it's like, okay, so what it means when like, yeah, when it's like I, right? So when it's a complex exponential.
I times itself, and multiplying by I has the effect of rotating numbers 90
Yeah,
degrees.
exactly.
So, as you might expect, things only make sense here if we start thinking beyond the number line and in the complex plane. So, even before you know how to compute e to the I times t, you know that for any position this might give for some value of time, the velocity at that time will be a 90-degree rotation of that position. Drawing this for all possible positions you
So I guess what it means, I guess what I'm saying is, uh, like you can ignore, like it just ignore the if we ignore the h bar thing and we just treat it as a constant, it's like 1 divided by h bar, whatever. So so the contribution of the propagator from a particular trajectory is e to the power of I times the action of that trajectory. So yeah, but I don't really know what that means. So other than it's a number that you can just interpret as a rotation. And then saying the contribution from each path. So the idea is that if you add up all the contributions of all the paths, you yeah, that's oscillation related exactly. It's just like I'm trying to I'm trying to not lose track of the whole chain of thought here, whereas like the propagator is the what defines sort of the probability, the transition probability between one state and the other state. This is, by the way this is defined, is that it's the integral of all the possible paths. The integral of what? Like the integral of it's this funky thing here, right? So it's the integral of, and this is just a projection of one state to another. Um, However, that can be integrated, right? But it's and so what and then that's then taken as a propagator. But then what Feynman's saying is that the contribution of each path to the propagator. So this means the probability that you will then associate in a path has this form. So it's dependent on the action, but in a way that the higher the action, I guess the bigger the rotation. I don't know, whatever that means, right? But like the rotation of this contribution, which is what it's going to end up being the complex amplitude of I don't know of like yeah what the propagator gives you, right, which is the transition coefficient or probability. It's not a probability directly, it's a complex number that then gives you the probability. but but yeah, so that is every possible path contributes with equal amplitude. Oh, okay, so what Feynman is saying is that every possible path contributes with equal amplitude to the propagator, but then with a different phase. Ah, I get it. Okay, so that's why it's e to the power of like, so that's the rotation here is then associated to the phase. But it doesn't seem so obvious to me that you would have equal amplitudes, right? Yeah, okay, no, you'd have okay, so no, so that's true. It's actually for each path contributes with equal amplitude. It's just that if you have multiple paths that go between the same points, you'll have higher amplitudes altogether once you add up things. But yeah, and because this is complex and whatnot, then probably paths can cancel each other, right? Um, so summing all over the possible trajectories, we arrive at the propagator. Uh, but how do you get there? That's the yeah, I don't know. How would you even conceptualize something like this? How would you even just like say, hey, this could be modeled like that? Even just the fact that like you think about paths and then you think about actions, right? There's a normalization constant that is independent of any individual path and therefore depends only on time. I guess this would make sure that all the contributions are up to one and all and whatnot. Um, so equation 4 is the heart of the path integral formulation. How this summation, which has to be well defined, is to arrive at the correct propagator is far from obvious. We now discuss some salient features of 4 and dive into the technical details of a simple example. Good, I like that. So how can it be that the infinite summable does not diverge? That the different phases are different phases are keys to these. So that's what I said, right? So because they're complex numbers, they can cancel each other. I think that's what this is gonna be saying basically. For trajectories between which the action differs by a delta s roughly pi h bar, the corresponding contributions will cancel. Uh, Contributions to the propagator from possible trajectories through a region far from the classical path would in the aggregate cancel. For trajectories between which the action differs by, but I guess this must be then trajectories between the same endpoints, right? So denote the classical trajectory XCL as the trajectory with the minimum value of the action XCL for classical, I guess, which is stationary to first order with regard to deviations, whatever that means. On the macroscopic system, this is trajectory observed with very little uncertainty. Right. On the macroscopic this trajectory observed with a very little uncertainty. Investigation of equation 4 gives the reason for these. Trajectories close to the classical one cause no first order deviation in the action and contribute with coherent phase to the integral. Trajectories with action pi times h bar more than the classical action are out of phase and interfere destructively with each other. Integrating over more and more such trajectories should cause their contributions to average out to zero. In this way, the classical trajectory is qualitatively important. In general, the region of coherence is related to the classical nature of the system. On the macroscopic classical scale, pi times h bar is a frighteningly small amount, making the principal contributing trajectories those in a narrow band around the classical one. Okay, so what this is kind of telling you, I guess, is that if you just take a look at the classical level, you can still think of all these different trajectories, but they're so small that you don't care. So they just, you can just assume things cancel, and just the kind of classical path is just overwhelmingly taking over. But I'm okay. Can skip that. Yeah, the propagator. So the propagator is because to see you're asking in the chat. So I think, I mean, the way they define it here, the propagator is just it's just it tells you basically the probability transition between 2 points, right? So if you think about like the wave function and parameterized as like position and time, so you kind of have like that's the propagator. So it's telling you that if you give it like 2 points, it will tell you, or two states, it will tell you what's the probability of that state transitioning to that state. That is then, I guess, what is in a way equivalent to the Hamiltonian in the Schrodinger picture, right? So the Hamiltonian kind of encodes how the system evolves, and then this is what the propagator is actually doing. Is just rather, is it just actually doing it differently? It's doing it with respect to a potential target change, right? Or target state, kind of. Free particle. For concreteness, we use the method above to determine the propagator. So now we're going to be working on a propagator. Okay, so for the simplest of systems, the particle moving in free space along one dimension. In this case, we will actually evaluate the integral given above over all possible paths. Although, as Mackenzie notes, after a similar derivation, often much of the study of the path integral formulation is concerned with how to avoid just these. Yeah, because it's probably too much work, right? With the complicated cases. So let xt describe a potential trajectory from from A to B, right? So xata to xbtb. We discretize the trajectory by dividing it into chunks of different times. Let's start a follow up. So we've got, where's my pen? So we've got time that, as I've learned, physicists love to make it flow vertical, and we've got position, and I should find better drawing software. I don't know how to draw straight lines. Cool. So you kind of discretize time, right? So you just take a look at some intervals, like you don't really care about in between. And are we discretizing position such that the intermediate points are, yeah, okay, so you're kind of discretizing position as well. So you're also going to do these. So then we'll just hope as n goes to infinity that it's all continuous. Okay, so it's a free particle, so we define the potential to be zero. The action depends only on the velocity, which between any t1 and ti and ti plus 1 is constant. So the action is just the velocity because it's the kinetic energy, which in this case is constant, right? Enjoy dinner time. Yeah, enjoy dinner time. Yeah. We're happy to talk path integrals. It can be in a distant future though. Let's see. So the action depends only on the velocity, which between any of these points in time is constant. We denote the action between ti and ti plus 1 by the following. Why integral? This is kinetic energy, isn't it? What's kinetic energy? Velocity. It's mass times velocity squared divided by 2. Mass times velocity squared, so it's the second derivative of position. No, it's the first derivative of position squared divided by 2. Know why we're integrating though, but well, so we get to these as the action. So to describe every path from x0 to t, x0, t0 to x and tn, we simply vary each intermediate point xi at each ti over the entire domain. As the x and h take a continuum of values from minus infinity to plus infinity, the sum of the contributions from every path Okay, so this just go straight and plug in Feynman's formula here of e to the power of like I divided by h bar times the action, which we've defined here. And in this case, so what we're saying is this is the action at time I, right? So for a path, you have to add all these actions. So you run through I1 to n. So The action depends on the velocity. So between times, the velocity is constant. So you're adding all these contributions, and there's a constant that depends only on the elapsed time. Kind of let 6 by integrating over one variable at a time. For convenience, let k be all these. Integration over the first variable yields it's far too late for me to do integrals. Okay, so you get to that. We ignore the constant term since it is absorbed into their normalization constant a. After a few more integrations, a pattern emerges which Feynman and Heaps illustrate more explicitly. Integrating over the first n spacetime points leaves a factor of k to n plus 1 x n minus x0 squared in the exponent after evaluation. Mm. So the value for a, blah, 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 blah. So you have these at the end, which is in fact a propagator of a free particle. A fascinating feature of this result is that U is composed of the contribution from the classical path alone. This is not always the case, and we'll discuss this phenomenon in section 3. What do you mean by these? That it's just as a function of like the I don't really understand that. I definitely don't understand that. Okay, that seems to be the example. Describing event described by the respective diagram. So, equivalence to the shrunk the picture. Yeah, I mean, what do you do with that? So you have the propagator between 2 points, right? So that should tell you what is the probability for the particle to travel between these 2 points. So, but this new formulation really is equivalent picture of the non-relativistic quantum mechanics. Schrödinger equation is differential. In differential form defines the time derivative of a given initial state. Blah, blah, blah. So within the record is differential equation using the path integral formulation. Consider the initial state psi, some infinitesimal time alpha later, and at some infinitesimal position way, the state can be described as follows. So now this is the So here you have a state and you multiply by the propagator. To calculate the propagator, we need to determine the action for a given position coordinate. The particle's velocity and position can be approximated as the propagator is in the limit. No, the propagator is in the limit as alpha becomes 0, the approximation above becomes exact. Therefore, we expand several of the quantities in 16 powers of these, and the exponential of the potential energy and the potential energy itself. That is definitely too hard. We keep the first two terms. Whatever. I'll have to go through that later again. Okay, so but basically, you kind of derive it. To recover the time derivative, we can rearrange the limit as. God, that is too dense. That is too dense for me now. Okay, let's take a look at the harmonic oscillator. um, but yeah, I guess at the end, what you're getting is these, right? So you're saying that this is just a time dependent equation. Okay, so there's other ways to see these, which is from the Schrodinger, you massage it into the Feynman's formulation, Feynman formulation. First principles of path integral method. Okay, so the harmonic oscillator. Okay, but let's maybe recap for a second. Okay, so what have we seen? What have we seen? So we've seen this. So we have the concept of the propagator that is basically telling you the possibility. So the propagator is what you want to calculate when you do the path integral stuff. And that's yeah. So that's what you want to do, and that's what then that sort of will be the equivalent to the Schrodinger equation. Mm, yeah, right, because it's telling you that it's giving you the relationship in general terms, right? It's just the Schrodinger equation tells you how is the energy, how are the energy, how is the energy changing, and so that allows you to find the wave functions that are solutions for that. Whereas the propagator is telling you, yeah, but the propagator doesn't tell you anything about the wave function, does it? Well, we'll see. Well, I guess we'll see now with the harmonic oscillator. But the normalization constant is independent of any individual path, and therefore, so we've seen this thing with the propagator. Talked about classical trajectory is a trajectory with the minimum value of the action s. That's how they call it, classical trajectory. I think that's a bit confusing because I don't know if that really is meant in terms of the classical versus quantum kind of thing. But then okay, so then we do. But that still keeps in, intriguing me. Essentially, what this is telling you is that right, is that you can apply the action concept. The action concept is just it's universal, right? It's just telling it's a quantity that tells you how much a system is changing. Um, and so and so in this case, that quantity applied as a complex exponent of E, when you're doing it like that, you're getting this kind of rotations of the phases, right? So you're saying that the action kind of can be at the quantum level complex, so things can cancel out and whatnot. Uh, but then you ultimately got to define this action, right? So and then we see an example with a free particle, and so where the potential is zero. So this means there's no potential energy. It's just the free particle goes at a certain speed, and that's the action. So so we define the action as the integral between ti and ti plus 1 of how position is changing, so of velocity, right? So yeah, so that's just yeah, cool. Then this is turned into that. And so to describe every path, we simply vary each intermediate point xi at each ti. So I guess these integrals are then these ones, right? But like this is like multiplied or what? I guess so. Or is it a sum? This is what I don't know. What is dot 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 here? So this is dx, so e to the power of I times the action. Times the action. So how the heck do you integrate that? Jesus. For me, it's like KB. This is just overpacked with notation because yeah, I can see. Okay, so this is just telling you from I to N, right? So from all um the moments in time, and then that you have. I guess what's confusing me is that this is here. The index are running here. So this is saying e to the power of k times this one. A pattern merges with Feynman and heaps. This is integrating over the first n space-time points is a factor of in the exponent after evaluation. That's this thing here, right? So we evaluate n minus 2 more integrations like that. What is the propagator? Okay, it's that integral that we've just done. So it's literally that. The value wave is contained when is obtained when okay. Yeah, I don't know. I'm kind of pretty much at the point just staring at the screen because I'm trying to make sense of these. Kind of like high level, I understand it. So the propagator is the thing, right? Yeah. So the equivalence to a Schrödinger feature is something that we don't really have to dig into at this point in time. Then the harmonic oscillator, what is it going on here? What's going on here? So now let the particle be in the potential given by these. So these, in principle, we could explicitly compute the propagator by considering a generic initial state and applying time evolution to each of the eigenstates. This way, it's algebraically brutal, requiring the summation of an infinite series of expressions involving Harmonic polynomials. Good. So we don't want to do that. So using the tools we have developed above, we will derive the propagator for the one-dimensional harmonic oscillator with a surprising lack of intense computation, relying instead on the theoretical basis of the path integral formulation. So, okay, that seems fairly simple. So we approach the problem in a slightly different manner. So let x CLT and x dot CLT be the classical path and its velocity, respectively. God, like when you just talk about velocities in here, it just lose me. I mean, it's so abstract. But yeah, the derivative of position, right? So we can represent any other path. We can represent any other path as a deviation from this one. Okay. So cool. So you take the path that's got the minimal action, and then you represent any other path as a deviation from this one. So with the correct boundary conditions, y and the first derivative of y are 0 at the endpoints of the path. Yeah, because of this feature, I never got to finish this. Because at the end of the path, like if this is the classical path, Like at the end of the path, the close to the edge of the path, there's just no difference. Yeah. Let's rewrite the Lagrangian for a generic path in a way that isolates the classical Lagrangian. We relax the time dependence since it's implicit. God. What is the Lagrangian now doing here? Uh, so what is now the Lagrangian doing here? Didn't the Lagrangian have to do with action as well? Okay, so this is about the equality constraints. The derivative test of an unconstrained product can still be applied. In order to find the maximum and minimum of a function of x subjected to the equality constraint g of x equals 0, form the Lagrangian function and find the stationary points of L considered as a function of x and Lagrangian multiplier. So this is a way to add constraints into these, but I really don't know what that means in this case. The first term in 23 is just a Lagrangian for the classical trajectory. The second term is 0 by the Euler-Lagrange equations. Since on a stationary path, this term must be 0 for any well-behaved deviation y. We will return to this later. The third term is a Lagrangian for the deviation. The action is separable in the sense that the propagator has the following form. Why? What are we doing here? Huh. I'm kind of reaching my limits of uh, going path across statistical mechanics. On top of that, go on. First term is organization. The second term is 0 by the organizations. Term is 0 by 0 for any well-behaved deviation. We'll return to this later. It can be shown that the integral over all paths depends only on the elapsed time and not on the position. Normalizing this expression is not trivial. Consider the composition of a deviation into its Fourier series of periods and then integrate over the components. We use the result, though there are other methods. This is the correct result. Later, when we investigate the connection between the path integral formulation and statistical mechanics, we will use this result to recover the energy eigenvalues. I think I need a coffee break. Yeah. I'm literally just staring at these, and it's complicated. So, because here the whole thing with Lagrangian just got me. Maybe we'll need to find so quantum harmonic oscillator propagator. So in Sakura, the derivation of the propagator leads to the expression which it says leads to the expression of the propagator by using the formula. So my discretization. Okay, so this is another this is another paper. Also live with external sources. There's a bunch of other systems. Mode expansion. So here they say the action of a one-dimensional harmonic oscillator with mass m is these. So they just go ahead and define the action like that. Where Ws is time-dependent circular frequency. To calculate the propagator from q prime at initial time t prime to q at final time t, we divide the time interval in n intervals. Our starting point is 2.35 with the following classical action for broken line path. Wow, that's definitely too complicated for me. Definitely too complicated. But getting somewhere, I guess. I guess that does, though, in a way, confirm my suspicion that, I mean, here you're talking about like the dynamic part of quantum mechanics, right? So the actual evolution. But that does not really tell you. The path integral really doesn't tell you anything about like entanglement per se, right? In terms of like the static picture of a state. But I saw this paper, entanglement. Ugh, I cannot write that. Entanglement from a path integral perspective. Oh. Okay, interesting. So, how most of the time takes on quantum mechanics are from health and mechanics. You mentioned the path integral as a side note. This makes it difficult for me to gain insight into common phenomena, like certain areas of optics. But I have one. Only see the entanglement explained from the perspective of eigenstates of Hamiltonian. Is it how? Entanglement from the perspective of eigenstates of Hamiltonian? I was wondering how entanglement would be interpreted if you start from Pythagorean formulation. It would be more than happy to hear from a quantum field theoretic perspective as well, but the usual quantum mechanical path integral would certainly satisfy my curiosity. So path integrals have been used to discuss entanglement of quantum fields. The path integral is used to trace out part of the system. The path integral is used to trace out part of the system so that the entanglement is given in terms of von Neumann entropy, in terms of the trace of the partial density matrix. You can find an example here, for instance. Hmm. Hmm. Space-time path integrals for entangled states. Maybe that tells me something. March 2021, fairly recent. What does the Although the path integral formalism is known to be equivalent to conventional quantum mechanics, it's not generally obvious how to implement path-based calculations for multi-qubit entangled states. Exactly. Whether one takes the formal view of entangled states as entities in a high-dimensional Hilbert space or the intuitive view of these states as the connection between distant spatial configurations, it may not be even obvious that a path-based calculation can be achieved using only paths in ordinary space and time. Previous work has shown how to do this for certain special states. This paper extends those results to all pure 2-qubit states, where each qubit can be measured in an arbitrary basis. Certain 3-qubit states are also developed, and path integrals again reproduce usual correlations. These results should allow for a substantial amount of conventional quantum analysis to be translated over into path integral perspective, simplifying certain calculations and more generally informing research in quantum foundations. Okay, so we probably will read into these. Single qubit measurements, quantum probabilities, measurement device, the 2-qubit path integral. So the main result of this paper is to show that the observable correlations of any entangled 2-qubit state can be computed from a path integral perspective using paths in physical spacetime. Thanks to the Schmidt decomposition, a generic 2-qubit pure state can also be written in the simple form. Here the constants A and B are assumed to be real and positive. The basis for each qubit in the above expression is fixed to the Schmidt basis, defined by basis A, but the below results are still generally applicable. The general case would merely require particular rotations of the measurement. So this is the different states. Probabilities of measuring. a second, I'm gonna get some coffee. Gonna go anyway soon. Okay, but whatever they do here is they just go through these calculated probabilities of measuring certain things. Okay, okay, so the analysis is then done probably as in like what are the measurement probabilities and whether we can see any correlations in that. And these probabilities are computed with the path integral formalism then, right? So you're saying, so what are you saying? So you're saying um, this is the state that I am in, then I apply a measurement, and then how, hmm, hmm. This is about three qubit states. So you have these probabilities. So this concludes the demonstration that any observable correlation of any entangled two-qubit state can be reproduced by a simple sum over paths calculation, where each path can be said to have a space-time representation. No higher dimensional configuration space has been required. Any observable correlation of any entangled two-qubit state can be reproduced by a simple sum over paths calculation. Yeah, I guess I'll leave it here, folks. Complicated. It's definitely more complicated than I thought. But yeah, we're getting somewhere. So yeah, so I guess it's got to do with same probability as quantum theory for these arbitrary two-qubit states. Is that, you know, so you're calculating the probabilities of the correlations, which is kind of what I like, right? Because it's what I also see is similar to what I was trying to do with the entanglement hypergraphs, right? Where you kind of correlate, you're correlating the states, really, because like the entanglement can also, doesn't really have to be at the measurement like level. You can, you can correlate things like saying when this qubit is in the plus state, these other qubits in the minus state. So you can calculate these probabilities, and that somewhat gives you whether you're entangled or not. It's confusing because what keeps confusing me then is the Wolfram's interpretation of these, of the entanglement being the parents are being shared in the multi-way graph. But anyway, that's probably been a really confusing session. Um, it started off well, but then I think that they lost me here with the Lagrangian thing, just because I've never done these myself. So I'd have to dive into these a bit more to fully understand that. But yeah, so there's this is just another way to do these, not like because with the free particle it's just brute force, do the whole integral stuff, right? And then find the propagator expression. But then how does this map to the quantum system thing? That is interesting, right? So you somehow calculate these probabilities. That probably would be the next thing for me to try to break this down a little bit more. See how this is formalized. It's just extremely complicated to break through, right? Because, and again, I'm not interested in learning the whole framework and everything that there is to learn, but it's just trying to understand how entanglement is or how can you model entanglement with path integrals. I guess we'll do that next time. Path integrals, spacetime path integrals for entangled states. Paths through Hilbert space, including paths that consist of pure entangled states. Because a single entangled state has no spatial representation of any of these paths, would also have no possible space-time representation. Approaches in Hilbert space paths are common in the literature. Okay, so and have been extended to quantum field theory. The central result of this paper is to demonstrate how the path integral can be applied to entangled states without requiring departure from the conventional spatial representation. Scare codes around path. The success of procedure is most evident for the case of the Which-way entanglement. That's complicated. Anyway, good. Yeah, see you next time. I'll try to get. I really, really want to get more regular. I know I say this every time, but I really want to get a regular schedule on these. Um, but yeah, so I'm just barely reading, barely making it. Like it's hard because you got to leave a lot of the detail away in order to progress, and then you'll probably come back to it later, and then but yeah, you have the propagator, and then this propagator tells you these, and then yeah. So you have this action that you have to define, blah 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 blah. I need to put all the things together. We should do like a refresh session soon. Anyway, bye bye.